This is our demo video for Senior Design 1, Group 8, Computer Assisted Robotic Eating Project. Our group consists of 4 computer engineers, Bao Ho, Shani May Ruiz, Tuyen Tran, and Queen Lee Siet. We have obtained all of our materials as shown on the right, including the MyCobot robotic arm, RGB camera, time-of-flight sensor, 3D printed end effector, Jetson Nano, LCD display, and foot-operated pedals.
This is our attachment that we 3D printed so that we could attach the spoon on the robotic arm. In this part, we set up the server for our Raspberry Pi, and the Jetson Nano was able to send the ping over the established IP network.
We obtained the Raspberry Pi CAM module and connected it to the first CSI port of the Jetson Aura Nano. For it to work properly, we had to hardware configure the Jetson CSI port to support a IMX219 camera through the terminal. This video shows the camera running a simple Python code that shows the view of the camera. We also successfully ran a basic face detection code that made bounding boxes accurately around human faces. The time-of-flight sensor was connected to our SDA and SCL GPIO pins, being powered by the 3.3V power line. This video shows the sensor running a code that accurately outputs the distance of our hand. We used a 15cm ruler to show the accuracy of the reading, with it resulting in an error margin of 0.1. Here we connected the buttons to each of the respective GPIO pins that allow the Jetson to read for an active low signal. Upon pressing the first button, the Jetson Aura Nano sends a feed message to the Raspberry Pi over the established server connection we made earlier. Then the Raspberry Pi receives this message and triggers the feeding phase, which emulates a scooping motion to feed the user.
Media pipe mouth detection was used for the task of detecting and tracking the mouth for spoon feeding. OpenCV and media pipe face markers were used to track up to 2 faces simultaneously by defining the outer and inner lip landmarks. Mouth openness ratio derived from lip height by mouth width, threshold of 0.08 for classification of mouth state, open or closed. Performance benchmarks were measured through measuring the detection time, total loop time, and average frames per second. One way this can be improved is computing the centroid of the mouth to gain the accuracy of the spoon feeding. We decided to use the YOLO V26 because of its efficiency and less computational power load on edge devices like the Jetson Aura Nano, which supports this project that requires real-time, high-accuracy detection. 430 images were split between 300 for training, 87 for validation, and 43 for test. The model saw the training dataset 300 times for 300 epochs. Metrics from the validation set reveals that the model has a mean average precision of 97.9%, which is a high detection score across all classes.
We decided to use apron tags to identify different sections of our plate. We will assign a unit tag ID to each of the sections so that the camera can detect the visible apron tags and display the corresponding tag ID in real time.
Here is the mobile application used for our system. The app controls the robot arm through Wi-Fi communication. The first page is the authentication page where users can sign up or log in. This allows them to securely access the system and keep track of their meal history. The second page provides different functions for user and caregiver. The user they can control the robotic arm and view their meal schedule. For caregiver, they can also control the robot as well as monitor and review the user's meal history.